and then we'll share screen. Great. So today I want to talk about the so-called Neumann series. And the Neumann series is a perturbative expansion of the solution of an integral equation about some initial function and the development of this perturbation theory. So really, we're going to be talking about perturbation series expansions here, and I'm going to give you an illustration of where this works in basic quantum mechanics. And as I said, this kind of Neumann series expansion forms the rudiments of what would be called Feynman expansions in quantum field theory. Are there any questions? Okay, so far we've talked about integral equations. We've classified the integral equations, which has helped us kind of arrange our techniques for solving them. And I've covered in the last lecture a series of what you would call special techniques. Right? These are ad hoc special techniques that you would use to solve various integral equations, and they really kind of depend very strongly on the kernel that's present in the integral equation. Okay, but at the end of the day, they're special techniques, and they're really ad hoc, and they work for a small set of integral equations. As I said previously, integral equations are like integrals, in as much as differential equations are like derivatives, right? In differential equations, there's more or less in the theory of differentiation, you get some rules and you apply these rules and everything goes well. But when you try to integrate functions, that's when really you've got to be very tricky about the techniques you use, et cetera, et cetera. There are, of course, some really powerful power tools at your disposal, probably the most powerful of which is the theory of complex analysis, which allows you to solve a whole really big class of integrals. But for the most part, you use a lot of special techniques that you have got over the years working with integrals. And integral equations are like this as well. So these special techniques are really only as good as the problems that they can be applied to. Okay. In this case, they're a really small set of integral equations that you can apply the special techniques that we learned in the last lecture to. In the same way that there are special techniques for solving differential equations, for integrating differential equations, and they apply to very specific classes of differential equations, and that there's a broad technique for solving differential equations, which is the Forbinius series solution method. There's a series solution technique that's essentially due to Neumann and Liouville and Volterra that we're going to study today. So, and this is based on making a series expansion for the unknown function in a linear integral equation. So let's start off by writing down such a linear integral equation. So I want to consider the I want to consider the linear integral equation given by phi of x equal to some known inhomogeneity f of x plus lambda times the integral from a to b of some kernel xt. Now we're not putting any constraints on what this kernel can look like. So it could be separable, it could not be separable, it could be translational invariant, it doesn't really matter. This technique is kind of agnostic about that. Right, so here's our linear integral equation, and we want to solve for the unknown function, in this case, phi of x. And this guy is known. It's given in the statement of the problem. Okay. Okay, very good. So this is a Forbinius type problem because the intervals are of integration are fixed. It's a inhomogeneous integral equation because of this f of x, which I'm going to assume is non-zero. So known function that's not equal to 0. So I very specifically want it to be this inhomogeneous problem. And it is of the second type because phi of x occurs both inside and outside the integral. Right. So my first guess at this is going to be that phi, okay, so here's what we want to do. We want to make a series expansion about some initial guess in the same way that when you solve, let's say, for the roots of an equation using Newton's, the Newton-Raphson method, you make some initial guess. And then you hope to God that this guess is good enough that your solution converges to the actual answer instead of diverges away from it. So that's roughly going to be our strategy here as well. So let's take it as a follow. Let's take the following to be an initial guess. So our first guess for a solution is, and I'm going to call this thing phi naught for initial guess. And I'm going to say that phi of x is going to be approximately this phi naught, and I'm going to choose phi naught here to be f of x. Now, I want to be clear about something. This choice is not mandatory. It's not compulsory. I don't have to choose phi naught of x to be f of x. But what it amounts to saying is that the second term is going to be small relative to the first term. So that's basically what we're saying here. This second term is small relative to the first term for my initial guess. That's what this choice amounts to. Okay. So I want to make the point here that this is not compulsory, but it is convenient. Okay. Let's see where this gets us. Well, if I take that to be my first guess, and I plug it back into the integral equation, at least I plug it back into the right-hand side of the integral equation, that says that in the integral equation, the following is true at the next, for a second guess. Let's call the second guess phi 1 of x. And phi 1 of x is then going to be f of x plus lambda times the integral, again from a to b, of this kernel k of x and t, times the first guess that I made. The first guess that I made was f of x. Sorry. Yeah, I made it f of x, which means that when I substitute here, I've got to replace this with f of t. That's my second guess. So I can, of course, I can, of course, iterate this and substitute this phi 1 into the right-hand side of the integral equation. And when I do that, I find that similarly, let's put it this way, iterating this, I get that phi 2, for example, is equal to f of x plus lambda integral from a to b k of x t f of t dt plus lambda squared integral from a to b twice k of x t1 k of x t1 k of t1 t2 f of t2 and then dt2 dt1. Okay, so all I've done is I've substituted phi 1 into the right-hand side of the integral equation, into the right-hand side of the previous integral equation, and iterated it through. And I can continue this. In general, I will find the following structure. I will find that my solution phi n of x at the nth level can be written as the sum from I equals 0 to n of the ith power of lambda times ui of x, where I'm using a shorthand notation, u1 of x is just f of x, u0 of x is f of x, u1 of x is the integral from a to b k x t f of t dt u2 etc. until I get to the kth u, or let's say the nth u, and this is equal to the nth integral. So there are n such integrals sitting in this expression. And n products of the kernel all the way through to tn minus 1 tn f of tn dtn through dt1. All right. And Sebastian and Nitin were doing my string theory course, where we spent pretty much this whole semester talking about perturbation theory, would recognize this immediately as how you construct the path integral iteratively. Okay. And provided this series converges, so if the series converges, and I'm not always guaranteed of this fact, but if it does, then our solution phi of x that we're looking for, the solution of the integral equation, is given by the limit as n goes to infinity of phi n of x. Is everybody happy with this, with the idea behind this? Yes? Good. That still might be a little bit difficult to visualize what exactly we're doing here and what this series means. So it helps to think a little bit of the integral equation in operator language. So let's go back to the integral equation we're trying to solve. I remind you, it's this one. And let's ask what this integral equation would look like in operator language. So in operator language, our integral equation looks like phi equal to f plus lambda k phi, where this k phi, where k phi here is shorthand for the integral from a to b of k of x t phi of t dt. Okay, so this is just a symbolic expression of what our integral equation looks like, and we understand that, you know, k acting on phi really means this integral. Now, in the same way that I can state the integral equation symbolically, I can solve the integral equation symbolically. So the solution of this integral equation is what I get when I take phi's all the way to the left-hand side and then divide through by 1 minus lambda k, which really means find the inverse of the operator 1 minus lambda k and act on it from both sides. So this is phi equal to 1 minus lambda k inverse acting on the inhomogeneity f. In other words, the Neumann series, which is this here, I should have written down. This is called the Neumann series. The Neumann series is nothing but the binomial series expansion for the operator 1 minus lambda k. Okay, so the Neumann series is a binomial expansion for this operator. Okay, and so now it kind of makes sense why we're making this expansion and why we chose a particular function to expand around, etc. And convergence of the integral series corresponds to whether or not such an inverse exists. Okay, so the integral series converges if the inverse exists. Okay, so is everybody with me intuitively as to why the series works and how the series works? Good. So let's do an example that might help clarify how this works in practice. So I want to use the Neumann series here to solve the type 2 Fredholm equation given by the following. So let's solve the Fredholm equation, phi of x equal to x plus 1/2 integral from -1 to 1 of t minus x times phi of t, tt. Okay, so here our inhomogeneity f of x is really just x itself. So let's guess then phi naught of x equal to x, in which case phi 1 of x is given by x plus 1/2 the integral from -1 to 1 of t minus x times t dt. I can certainly do that integral. Remember, x is fixed in this case, and this is x plus 1/2 of 1/3 x cubed minus 1/2 t squared x, and I have to evaluate that from -1 to 1, and that is just x plus 1/3. And so that's what phi 1 is. So again, phi naught is x, phi 1 is x plus 1/3. And you can continue with this iteration. So similarly, we find that in general, u u to n of x, it's not, it's equal to yeah, okay, so u to n of x is equal to x minus sum and this runs when n is greater than 1, greater than or equal to 1. From k equals 1 to n of -1 to the k, 3 to the minus k, plus x times the sum from k equals 1 to n -1 to the k, 3 to the minus k, yeah, which simplifies to x plus x minus 1, sum from k equals 1 to n of -1/3 to the k. And that's just a geometric series, and you can sum the geometric series and then in the limit, and then take the limit as n goes to infinity. And in that limit, we find that our solution phi of x is the limit as n goes to infinity. Let's make a note here. This is a geometric series which can be summed. So this is the limit as n goes to infinity of phi n of x, which you can show is 3/4 x plus 1/4. And I'm going to leave as an exercise for you to fill in the gaps. Okay, so that's how you solve a particular type of linear integral equation using the series expansion method. Now, as I said earlier, to anyone who's taken at least an introduction to quantum mechanics, this Neumann series expansion should ring some bells. And the familiarity that you're feeling is because this is exactly how we would compute time-dependent perturbations in quantum mechanics. And it forms the rudiments of the theory of Feynman diagrams in quantum field theory. So let's explore this a little bit and at least show you what it is what I'm talking about. So the Neumann series expansion is used extensively in quantum mechanics in the context where it is called time-dependent perturbation theory. So there, in the quantum mechanics context, we solve for what's called the time evolution operator. So the time evolution operator in quantum mechanics. I'm listening.
Could you just go back? I was finishing.
Oh, sorry. So the time evolution operator in quantum mechanics has a very particular form, and the time evolution operator is related to the Green's function of the Schrödinger problem, but we don't need to explore that much. That was just for Sebastian and Nitin's interest. Cabello, are you done?
Yes, I'm done. Thanks.
Okay. The time evolution operator tells you how to evolve states in Hilbert space starting from some initial state. And it's written as U of t and t naught. So starting at some time t naught and ending at some later time t. This operator is given by the identity, or 1, minus I over h bar, integral from t naught to t of v of t1 u of t1 t naught dt1. Here, v is some perturbing potential to the system. And t1 is some intermediate time, and then you integrate over all the intermediate times from t naught to t. And so what we've learned is that we can iterate this in the same way that we just did to find that u of t naught is equal to 1 minus I over h bar integral from t naught to t of v of t1 dt1 plus I over h bar squared integral from t naught to t dt1 integral from t naught to t1 of v of t1, v of t2, etc. Okay, so this is clearly of the Neumann form. U equals 1 minus I over h bar v plus I over h bar squared v squared, etc., 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 in the operator form. Okay, so far we've explored the Neumann method for the Forbinius integral equations, where the endpoints of the integrals are fixed, but there's nothing really stopping us from applying it to Volterra type integrals of the second kind, where we replace b with x in the upper limit of the integral. And in this case, in those cases, the Neumann series will converge for all lambda as long as the kernel k of x and t is square integrable. So let's make a note of that. The Neumann method will also work for Volterra integral equations as long as k of x and t is square integrable. Okay. So in the last 10 minutes, I want to introduce another do I want to introduce another idea? No. Okay. So let me stop here. Okay. So this should be, let's see. Yeah, okay. So let's stop here, and I will continue with one more lecture on symmetric kernels and Hilbert-Schmidt theory, and put that up on Vula. Okay, so this is the last official lecture for the module. I want to thank all of you who stuck it out to the end very much, for sticking it out to the end. It was wonderful to have Eric in the class as well. And it would be really nice if we could at least turn on our cameras for the end of the course, and just so that we can see who's been here. Very good. Fantastic. All right. Thanks, everybody. It was a it was a pleasure teaching the class as usual. And for all the UCT honors students, you must all feel a great sense of relief now that you finished your presentations. And I wish you the best for your exams. And for those of you who will hopefully be doing masters with us next year, I look forward to seeing you when in person is a thing again. All right. Thanks, everybody.
Thank you.
You.
Bye.
Bye.
Right.